Okay. So then there is just one small thing which is remaining, which is this ideal Boltzmann gas. First, let me describe the ideal Boltzmann gas and then we will see what it means. So in this case, of course, we have our energy levels, okay, beside and P. So the question that we are asking is the following. Okay? So it is the following. If you recall, in the last lecture, we had shown this is my temperature. So this is the ideal Bose gas. And this is the ideal Fermi gas at low temperature. And as you increase the temperature, they both start to become similar. And eventually, at very high temperature, you get the ideal gas law. So now the question that one asks is there a gas, some imaginary gas that one can imagine for which I don't have to take any limit? At any temperature, I will get the ideal gas. What is that gas like? What sort of quantum gas do I have to consider, which is neither Fermi nor Bose, such that at any temperature, I will get PV is equal to NK. And that gas is known as the ideal Boltzmann gas. So an ideal Boltzmann gas is defined by the canonical partition function of the Fermi type. We will see why it becomes like that. So this is the canonical partition function. What I have is I have NP particles such that the sum is equal to n. And for the canonical one, I have to put in the energy factor, which would be like this. And then I need to put in a factor here. Okay. What is that factor? Such that if I do the calculation, that is, I compute the canonical partition function, the planned canonical partition function, average average number of particles, average energy, and I get PV equal to NKBT. What is the factor that I need to put in there? It turns out that the factor that you need to put in here, it has to be of form by P of NP factorial. We will see that why that factor is required, but the claim is that if you put in such a factor and do the calculation, you will recover the ideal gas law. How? So that is what we are going to see. So suppose you do that, then what you get is you get this. Of I of P of P to the minus beta epsilon P NP divided by NP factorial. And so I just substitute it there. This is what I get. But this one is nothing but the, if I take this quantity to the power minus beta epsilon 1 plus e to the minus beta epsilon 2 plus e to the power whole to the power n. And if I ask what is a general term of this binomial, this series, what does it look like? This would look exactly like this. This we can prove in a minute, but this one is nothing but 1 by n factorial of summation p e to the minus beta epsilon p equal to the power n. This you can easily prove because what will be a general term of this series look like? It will look like e to the power minus beta epsilon 1 whole to the power n1 divided by n1 factorial, e to the power minus beta epsilon 2 whole to the power n2 divided by n2 factorial, all the way up to the last term, but then with the constraint that n1 plus n2 plus n3 plus dot 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 equal to capital N. Okay, so what I'm using is this formula. A plus b to the power n, a general term of this one will be what? It would be n factorial by p factorial, q factorial, r factorial dot 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 of a to the power p, b to the power q. Let's say plus c plus dot 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 to the power n. This would be a to the power b, b to the power q, c to the power r, all the way to sum over all possible values of p, q, r going from 0 to n with the constraint that p plus q plus r plus dot 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 that is equal to n. This is the binomial expansion. You can check for n equal to 2 if you have two terms. This is the general formula, so I just used it here. So therefore, we find that the canonical partition function of this Boltzmann gas, it writes like one divided by n factorial of summation over p to the power minus beta epsilon p equal to the power n. This is what it looks like. Now, let us evaluate this quantity. We know what we have to do when we go to the thermodynamic limit. We have to replace this summation over p by an integral. So if you do that, then we know what I have to do. I have to do this p epsilon g epsilon times e to the power minus beta epsilon. Okay, and g epsilon we know how does it look like. Looks like v by 4 pi square of 2m by h bar square whole to the power 3 by 2 of epsilon square. If we just substitute it here, I get this to be equal to this one to be equal to v divided by 4 pi square of 2m by h bar square whole to the power 3 by 2 of 0 to infinity of 3 epsilon epsilon to the power half e to the power minus beta epsilon. But this one I can easily evaluate using gamma function by doing the transformation x is equal to beta epsilon. So if I do that, what I get is b by 4 pi square 2 m kbt pi h bar square whole to the power 3 by 2 of square root of pi by 2. And so if I do the cancellation, so what I get is this is nothing but V divided by lambda thermal Q. So therefore, this canonical partition function, it is nothing but 1 by n factorial of V divided by lambda thermal Q whole to the power n. Why do I get this whole to the power n? Because I just evaluated the bracketed term here. So therefore, I need to do V by lambda thermal cube whole to the power n to get the canonical partition function. So once I know the canonical partition function, then it is quite easy to compute the grand canonical partition function. Canonical partition function, that would be what? That would be summation n going from 0 to infinity of z to the power n times z of nvt. So therefore I need to do 1 by summation over n 0 to infinity. I just substitute from there z by z to the power n by n factorial of v by lambda thermal cube whole to the power n. But this is nothing but e to the power of z v divided by lambda thermal cube. So this is the definition of an exponential function. So therefore, the grand canonical partition function has a very simple formula. So therefore, I get PV that is equal to KBT log of the grand canonical partition function. And if I take the log of that guy, I get KBT then B divided by lambda thermal cube. The next thing that I need to compute is what is the average number of particles in the system. That is given by Z tilde Z of log of Q of ZVT. So what I have to do is I have to first take the log of this guy. So that gives me ZV by lambda thermal Q. Take the derivative with respect to Z. You get V by lambda thermal cube and then multiply by Z. So this guy will give me ZV divided by lambda thermal cube, which is exactly what is coming out here. So therefore, this is nothing but N average. So therefore, we get this very interesting result that this is within the grand canonical ensemble, but this N average in the grand canonical ensemble is the actual particle number in the canonical ensemble. That is how I am going to fix the value of Z. This we discussed. So therefore, this is nothing but this is the n kBT in the canonical ensemble. So therefore, we could recover the ideal gas law. PV is equal to n kBT for the Boltzmann gas. So what is the definition of a Boltzmann gas? The Boltzmann gas, it doesn't exist in nature. In nature, quantum gases can be either a Fermi type or a Bose type. How do I define the Boltzmann gas? We defined it this way, that ideal Bose gas and ideal Fermi gas, when I take them to very high temperature, they behave like classical gas. So therefore, I have to take the Fermi gas and the Bose gas, take the limit T going to infinity, then I recover the ideal gas equation, PV is equal to NKBT. Now I ask, is there an imaginary gas that I can imagine for which I don't have to take the limit T going to infinity and I get PV is equal to NKBT at all temperature. And that gas turns out to be this ideal Boltzmann gas. You see why we never took any limit here. For the Bose gas and the Fermi gas, we have to take the limit of T very large, T going to infinity, so that Z is very small, and therefore we have to do Taylor expansion in Z, assuming Z to be much smaller than 1 in order to recover the ideal gas equation. Here I don't have to take any limit, but this gas is imaginary. It doesn't exist in nature. In nature, we have either ideal Bose gas or ideal Fermi gas. Okay. So are there questions on this part?
No question, sir.
Okay. So tell me if there are questions on the overall course, because what I'm going to do now is probably to give a summary of the whole course. But before that, let me ask you if you have if you have any question on the overall course.
Sir,
Yeah.
sir, chemical potential of photons, phonons, and other particles.
Sorry?
Chemical potential value for photons and phonon gas.
Yeah, so it is not, you don't need the chemical potential. Why you introduce chemical potential? You introduce chemical potential if there is particle conservation. Because you fix the average number of particles by fixing the value of the chemical potential. Now, if you do not have any conservation of particles, which is the case for photons and phonons and so on, then you don't need the chemical potential. Your grand canonical and canonical ensemble, they are the same because you don't have to have any particle conservation. So mu is equal to 0 there.
Okay, sir. Thank you, sir.
Yeah, any other question?
Sir, no, sir.
Okay, so let me take, whatever time is left, let me just do a summary of the whole course so that you remember, what is the way that we took to go from one part to another. Shall we do that? I mean, probably it will give you an idea of the overall course. Okay. So what we did was we started off with thermodynamics. Where we learned about such concepts as infinitesimal work done, infinitesimal heat absorbed, and we saw that these are path-dependent quantities. We learned about quasi-static transformation. And we saw that this one comes in two varieties. It is either a reversible transformation or irreversible. Transformation. We saw that when you take the difference between the two, this becomes a quantity that is path independent. U is a state function. U doesn't any longer depend on the path that one takes to go from one state to another. This we saw. What was the next thing that we did? We said that suppose I have a transformation that is quasi-static, yet reversible, and moreover, it is a transformation that is cyclic. It takes the system starting from one state back to the starting state. We saw that this quantity, if it is a quasi-static reversible transformation, is equal to 0, while if it is a quasi-static but irreversible transformation, it is less than 0. This led us to introduce this quantity called the entropy, or like this. So if T cross Q is the heat absorbed by the system in undergoing a reversible transformation, then D cross Q is TDS, where TS is the change in the entropy of the system. So this is what we learned in thermodynamics, and therefore combining this and that, we learned that EDS is equal to DU plus D by W. Okay. So then what we said was that, okay, these are known thermodynamic laws. These are verified in experiments. But the question that we ask now is there a way to understand these quantities in terms of the microscopic variables, namely the coordinates and the momenta of the particles? Okay. So there lies the importance of statistical mechanics. So the way we approached the statistical mechanics is, first we talked about the isolated system. So it was completely isolated. It has a fixed number of particles, fixed volume, and energy between E and E plus delta. So these are the macro state of the system. So we saw that corresponding to this macrostate, you can have many different microstates. These are given by the values of the momenta and the coordinates of the particles making up the system. So a convenient way to represent these microstates is to consider this 6n dimensional phase space, where each microstate is a point, and there are many points. So then what is the next idea that we introduced? It was the idea of the phase space density. That we said changes as a function of time. Why? Because the QIs and the PIs change as a function of time according to the Hamilton equations. Therefore, rho changes as a function of time according to the Whewell equation. The next thing that we introduced is the value of an observable as a function of time. So this is just given by an average with respect to the phase space density. And then this quantity, when in thermodynamics, we deal with equilibrium, when properties don't change as a function of time. So when this one doesn't change as a function of time, it has to be that rho doesn't change as a function of time. And when can rho not change as a function of time? When it Poisson commutes with h. So therefore, we came up with this idea that equilibrium in this setting, it means just that rho equilibrium also commutes with h. Microcanonical equilibrium, this is microcanonical equilibrium. Rho equilibrium is just a constant. It's just the inverse of the number of microstates which are accessible to the system. Once I know this quantity, what is this gamma? It is just the normalization constant. So what I do is that I do d pi dq by provided, of course, the microstate has the right amount of energy. Once I know this quantity, then the entropy of the system is defined to be this way. And once I know the entropy, then everything is known. Because the temperature is just defined to be the derivative of entropy with respect to energy. Threshold is defined to be the derivative of entropy with respect to volume, and chemical potential is defined to be the derivative of entropy with respect to number of particles. So therefore, within the microcanonical ensemble, the thermodynamics is very well established by following this procedure. So then what is the next thing that we did? What we did is to ask, the system is in microcanonical equilibrium, but what if I go to a subpart of this system? That subpart is exchanging energy. It is no longer isolated. It is exchanging energy. And for this one, what is equilibrium like? So that gives us the notion of the canonical equilibrium. This will be equal to e to the power minus beta h divided by the canonical partition function. What is the utility of the canonical partition function? The utility is that once I know the canonical partition function, I take the log of it and multiply it by kBt with a minus sign. This gives me the Helmholtz free energy of the system. And then what is the last thing that we did is if we go up to a subplot of this canonical ensemble and ask what is the equilibrium state for this guy, that is the grand canonical ensemble. The grand canonical partition function. What is the definition of this grand canonical partition function? This guy is nothing but e to the power beta mu n of z of mvt. So this is all that one has to learn basically in equilibrium statistical mechanics of classical systems. For quantum systems, things are very, very similar. We have to define a density operator. So for the given macro state, we first find out the state of consistent microstate. We have the whole collection, we find out what is the probability of occurrence of the kth microstate, which I denote by pk, and then this guy is defined to be this quantity. Pt, they evolved according to the Schrodinger equation. Therefore, if I use it here, I get the quantum Liouville equation. It is the quantum analog of the classical Liouville equation. And again, equilibrium would mean, here of course, if I have to know the average value of an observable, I have to do this operation, trace of rho times O, where I have to do averaging with respect to quantum randomness that is contained in computing the quantum expectation. And then I have to do an averaging of because of the fact that I do not know which precise microstate the system is in at a given time. Now this guy is a function of time because rho is a function of time. So therefore equilibrium would mean that rho becomes independent of time, which from this equation means that rho in equilibrium has to commute with the Hamiltonian. So therefore, I have again the three ensembles. Everything is exactly the same. I have the microcanonical ensemble, the density operator is I divided by gamma NVE. And the canonical ensemble where the density operator is e to the minus beta h divided by the partition function. And this, by the way, is given to be trace of e to the minus beta h. And then I have the grand canonical ensemble, the rho is e to the beta mu n minus beta h divided by the grand canonical partition function. And how is this going to defined? This is defined to be equal to summation of n0 to infinity to the beta mu n times the canonical partition. This is all that is there in quantum statistical mechanics. Then we dealt with ideal quantum mechanics. Ideal means there is an interaction between the particles. There is only kinetic energy contribution to the energy. So we talked about two types of quantum gas, Fermi gas and Bose gas. Fermi gas, what is the feature? The feature is that, first of all, it's a non-interacting gas. So what I can do is that I can find out the energy levels of the single particle system and start filling them up with particles. So I have the energy levels of the single particle system, I start filling them up with particles. For fermions, I have the rule that in no energy level can I put more than one particle. I can have either 0 particle or 1 particle, but not more than that. In the case of Bose gas, there is no restriction. I can put 1, 5, 50, 500, as many particles as I want in any energy level. So these are the two different types of quantum mechanics, ideal Bose gas, ideal Fermi gas. For both of them, we computed within the grand canonical ensemble an expression for the average particle number, average energy, and pressure times volume. And what we found is that both the Fermi gas and the Bose gas, when taken to very high temperature, behave like ideal gas. PV is equal to NKBT. This is the equation of state for an ideal gas. And this is the behavior that we recover from Bose and Fermi gas when I take both of them to very high temperature. Then we asked, is there an imaginary gas that I can think for which I don't have to take the limit T going to infinity, which at any given temperature gives me the equation of state as that of the ideal gas, PV is equal to NKBT. And the answer turned out to be the ideal Boltzmann gas, for which we computed the partition function in an ad hoc manner. I mean, ideal Boltzmann gas does not exist in nature. It is something that we imagined. And we found out that indeed for the ideal Boltzmann gas, I don't have to take any high temperature limit. At any temperature, it reproduces the ideal gas equation, PV is equal to NKB. And the last thing that we talked about is the Bose-Einstein condensation, which is the fact that if you take a Bose system and start reducing the temperature, then below a certain temperature, all the excited energy states of the system get occupied to their fullest extent, and therefore the extra particles start filling up the ground state. Okay. So we saw that Bose-Einstein condensation, it is a phenomenon that occurs only in dimensions higher than 2, that is in 3, 4, 5 dimensions. It does not take place in 1 and 2 dimension, and that has to do with the fact that we have the particle density given by two pieces, a first piece and a second piece. The first piece is the one containing the Riemann zeta function in 3 dimensions. And as incasity hit its maximum possible value, which is 1, is the Riemann zeta function contribution saturates. It gets to its maximum possible value. And then in order to satisfy the equality, contribution has to start coming in from the ground state part. And indeed, the ground state part starts to get diverging contribution. That is to say that extra particles could go and sit in the ground state. It has infinite capacity to accommodate any extra particles. Okay? And yeah, I think that was all that I talked about. Of course, there are many more things that one can talk about in statistical mechanics. We did not even touch that subject of how does a system approach equilibrium. We always assume that the system is in equilibrium, and then we study the properties of the system in equilibrium. but we did not touch upon the subject of how does the system approach equilibrium. This comes under the purview of kinetic theory. So kinetic theory is a subject in itself, and it requires, of course, a full-length course to explain how does the system approach equilibrium. This we did not touch upon because it's a very um, um, it requires several at least 10-15 lectures to make you understand how does one do the calculation there. Uh, yeah, we did not touch upon contemporary topics like superconductivity and all, again because of lack of time, because in 8 lectures, I mean, to introduce superconductivity and to talk about statistical mechanical treatment of superconductivity, well, again, it will take away a lot of, and it requires a lot of. So I think we can, so this is all that I have to say. So maybe in the remaining time that I'm left with, let's see if you have any questions that you would ask, that you would like me to answer.
Sir, hello, sir.
Yeah.
Sir, what are the major significations of three ensembles?
What are the, sorry, what
What
are
are the major significations of three ensembles?
significance?
Yes.
Okay. See, microcanonical ensemble is the most basic ensemble. So in microcanonical, you conserve number of particles, volume, and energy. But then the problem with microcanonical is that it has too many constants, too many constraints. So to do calculation, you have to remember that the total number of particles has to be equal to n, total volume has to be v, and total energy has to be e. So what happens is when you relax such constraints, analytical calculation becomes simpler. So first you relax the constraint on the energy. So you say that energy can be anything, but I will just fix the average energy. Average energy is fixed by the temperature. So the ensemble that you get where average energy is fixed, but energy can fluctuate is the canonical ensemble. Then you go to the case where you say that my energy can fluctuate, number of particles can fluctuate, but I will fix the average energy and the average number of particles. But the actual number can fluctuate, actual number of particles can fluctuate, actual energy can fluctuate. And that is the ensemble, that is the grand canonical ensemble. And in fact, in reality, the kind of systems that we study using statistical mechanics, let's say this piece of chalk, it does not have either a constant number of particles or a constant energy because it is constantly interacting with the outside environment. So therefore, grand canonical is the right ensemble to describe this chalk. But to derive grand canonical ensemble, we have to start from microcanonical ensemble simply because microcanonical ensemble starts off from classical mechanics. So you have classical mechanics and then closest to it is microcanonical, and then you start relaxing the constraints, make things more easy to deal with analytically, and you end up with the grand canonical ensemble. Okay,
Thank you, sir.
other questions?
Hello, sir.
Yeah.
In generally, what is the relation between statistical mechanics and thermodynamics?
Okay. Thermodynamics is laws derived from experiments. No theoretical basis. Statistical mechanics provides the theoretical noise. Thermodynamics, there's some laws derived from experiments. You don't know why they are, how they are, and so on. You just you do some experiments, you get certain laws. What statistical mechanics tries to do is to explain what you observe in experiments in thermodynamics on the basis of microscopic quantities like particle coordinates, particle moment, and so on. So in this sense, thermodynamics is like the experiment and statistics is like the theory. Okay?
Thank you, sir. Thank you, sir.
Any other question? So if there are no other question, then let me thank you all for listening to the lectures. So I have already shared the lecture notes with,
Sir,
yeah,
sir, can we find the density matrix by using the previous equations?
which one? Which equation? Yeah, indeed. I mean, the MCD matrix is just like this, no? You have to find the size. If you find the wave vectors and pk, then this is the density matrix. Is that what you were asking?
Yes, sir.
Yeah, so as I was saying, I have already shared the lecture notes with your, Professor Lakshmanan and your head of the department. Uh, so they will probably share with you the lecture notes and the videos also I will upload. I have asked our system administrator to upload them, and once the link is ready, then I will share with you. Okay, so you can view the lectures and also go through the lecture notes. And if you have questions, then you can always write to me and ask me by email, and I will try to answer them. So I think that is all. So thank you very much for coming to the refresher course, and I hope you found my lectures useful and you will go back and read books. Please do read books. I think it is very important to read good books. And I told you, Carson Wong and Enrico Fermi, they are two books which I strongly recommend. So these books, Fermi for thermodynamics, Fermi for thermodynamics, and Carson Wong for statistical mechanics. Please do read these books and also look at my notes. And if you have any questions, then you can send me an email and I'll try to answer. Okay. So thank you very much and see you again at some other time.
Thank you, sir.
Thank you.
Sir, you guys are the two notes materials, lecture materials. It is shared already. And
Okay.
good afternoon to all. I am happy to thank Professor Samik Gupta sir for delivering 8 wonderful lectures for the benefit of us on my own behalf and on behalf of the Professor Lakshmanan sir and Science Academies and the college management, principal and the staff members of our department and the participants. On my own behalf, I would like to thank Professor Samik Gupta sir for sharing his valuable time with us. Thank you, sir.
Thank you very much for the invitation and everything. Thank you very much. Thank you.
Thank you so much, sir.
Thank you. So I'm ending the Zoom. Shall I stop the recording?
Yes, sir. Yes, sir. Yes, sir. Thank you very much, sir.
Yeah, thank you.